Okay, welcome to Let's Get to the Marks. We're looking at AQA A-Level Chemistry, Paper 3, Friday the 23rd, 2023. I found this paper on the PMT website. You can get it on the AQA website as well. The code for it is 7405/3. Let's get into it. Section A, question 1. Ethyl ethanoate can be made by reacting ethanol with ethanoic acid in the presence of concentrated sulfuric acid. So here you can see we've got the skeletal formula for ethanol. It's reacting with ethanoic acid, skeletal formula as well, reversible reaction, and we're making ethyl ethanoate. And of course, this is a condensation reaction. We are releasing a molecule of water. Here we have the method. A mixture of ethanol, ethanoic acid, and concentrated sulfuric acid with anti-bumping granules is heated under reflux for 10 minutes. The apparatus is rearranged for distillation. The mixture is heated to collect the liquid that distills between 70 and 85 degrees. The distillate is placed in a separating funnel. The aqueous sodium carbonate is added and a stopper is placed in the funnel. The mixture is shaken, releasing pressure as necessary. The lower aqueous layer is removed and the upper organic layer is placed in a small conical flask. Part 6, anhydrous calcium chloride is added to the sample in the conical flask. The flask is shaken well and left for a few minutes. 7, the liquid from the flask is redistilled and the distillate is collected between 74 and 79 degrees. Woo, that was serious. 1.1, state the role of the concentrated sulfuric acid in the reaction, 1 mark. So we can see here we used concentrated sulfuric acid in step 1. Also in the mixture was the ethanol and ethanoic acid. So if we come up here and look at this, ethanol's a reactant, ethanoic acid's a reactant. They've combined. There's nothing here that the sulfuric acid you can see has directly influenced on that. The sulfuric acid, of course, is acting as a catalyst, lowering the activation energy. So catalyst, that is the role of the sulfuric acid. You could say lowering the activation energy as well. All right, let's move down to 1.2. 1.2, the reaction mixture is flammable. So ethanol, alcohols, flammable fuel, suggest how the reaction mixture could be heated in step 1. We don't want the ethanol, which is going to be quite volatile, have quite a low flammability point or whatever it's called. It's going to catch a light quite easily. So the apparatus, how are we going to heat it? Obviously not with a naked flame, with a Bunsen burner. That's going to cause the ethanol to catch a light. So if you don't want a Bunsen burner, what are you going to use to heat more gently or without chance of your reactants catching a light? And of course, we're going to use like an electric heater here. So I'll just use like an electric heater, no naked flame, e.g. Bunsen burner. So let's not expose it to a naked flame. Let's not have a big fire in the lab. That sounds like a good idea. Okay, bosh. 1.3. Let's shrink that down a little. And again, so we can actually see what's going on here. 1.3, figure 1, that's this figure here, shows how a student set up the apparatus for reflux in step 1. So this is the reflux where we've got the ethanol, ethanoic acid, we've got the catalyst, the concentrated sulfuric acid, we've got anti-bumping granules in there as well. You should assume the apparatus is clamped correctly. So we've got clamps on here. Identify 2 mistakes the student made in setting up the apparatus. State the problem caused by each mistake. So we're heating it up here. We've got this bung in the top here. And the problem with this, it's sealed tight. There is no area to release pressure. And so you could get an explosion. So mistake 1, the reaction vessel is completely sealed. So pressure, well, that's the mistake. And the problem is pressure build-up could explode. I'm not talking about like bomb explosion, but yeah, you could have the lid fly out and your contents go everywhere. So that's going to get us 2 marks. It did say there's 2 mistakes and we need to say the 2 problems. So I'm going to scroll down for the next one. So we've got a second mistake and the problem caused. So what the problem is here, yikes. This can be confusing sometimes. The water is coming in here. Sometimes that's not a bad bet. It's away from the heat source, but the water's coming in here and traveling down here. Generally, you want the water to come in from the bottom on all condensers. You want the water to come in from the lower point and push up to the higher point. The idea is if the water comes in here, it will completely fill the condenser. And what you'll get there is an efficient transfer of heat energy from the vapor to the water, and that means that you're going to get a more efficient heat transfer. Your vapor is going to condense better, basically. So, but the thing that's always on the mark scheme is that if the water is at the lower point, if the water enters at the bottom and leaves at the top, you will completely fill the condenser, and that's always on the mark scheme. Sometimes countercurrent flow is mentioned on the mark scheme, but that is where you want your vapor going in the opposite direction to the water, essentially. So that we're not going to look at that for this one. We're going to say mistake, um, mistake, water enters from above. Um, it should enter from below. So you want the water to come in at the bottom on these. It doesn't matter whether it's horizontal or vertical. The water should always enter from the low point. And the problem caused here is the water will not completely fill the condenser. So it won't fill the condenser completely. So um, heat transfer will not be as efficient. Groovy. That's quite common on these questions on practical apparatus. Okay, let's sing down. Right, we've got 1.4. State why sodium carbonate is added to the distillate in step 4. Explain why there is a buildup of pressure in the separating funnel, and that's worth 2 marks. So what you've got to ask yourself here is, what do you know fundamentally about sodium carbonate? What type of compound is that? Well, sodium carbonate is a base. Back in old school GCSE content knowledge, you should know that. And what a base is good for? They're good for neutralizing acid. And what acid do we have here? Well, if we have more ethanoic acid than ethanol, we're going to have excess. It's a one-to-one reaction, but if we have slightly more moles of ethanoic acid in our reaction mixture, we're going to end up with excess ethanoic acid. So this sodium carbonate can get rid of it. We can also use the sodium carbonate to get rid of the sulfuric acid. So the idea here is to neutralize either sulfuric acid, that was our catalyst, or ethanoic acid excess. So we might have ethanoic acid in excess. We want it to neutralize. Now, why would this cause a buildup of pressure in the separating funnel? Think about carbonates. So you should all know, for example, if I have sodium carbonate, oh my days, if I have sodium carbonate, let's go plus sulfuric acid. I could have written ethanoic acid here. Then what are we going to make? We're going to, oh my gosh, I can't even spell carbonate. Put a B there. Right, we're going to make sodium sulfate. And of course, we're going to make water, as you do with all these neutralization reactions, and we're going to make carbon dioxide. And what do we know about carbon dioxide? It's a gas. So you might remember all of that from GCSE. So we want to say CO2 released is a gas, will increase pressure. Cool. Lovely jubbly. So the main thing is that CO2 is a gas and we're using the sodium carbonate to neutralize excess acid. So those are your 2 main marks. I've put a bit of extra whiffle waffle there. Right, 1.5. Give a reason why 2 layers form in the separating funnel. Cool. Give a reason why 2 layers form in the separating funnel. Suggest why ethyl ethanoate forms the top layer. Right. Well, we get 2 layers forming. Look, we've neutralized. We've got water present now. Remember, it's a condensation reaction and we've got water. Remember, we've also had water produced with the sodium carbonate, removing the excess acid. So we've got water there. So the reason is ethyl ethanoate is not fully, I can't spell this next word, miscible with water. So it doesn't fully mix with water. Okay. So we get 2 layers and why would ethyl ethanoate go on top of the water? So ethyl ethanoate is less dense, is the less dense layer. So you normally get layers formed when one substance is less dense than another, then it's going to float on top. So ethyl ethanoate is going to be less dense. That would be our suggestione. Right. Next question, 1.6, state why anhydrous, the clues there, right there in that name, isn't it? State why anhydrous, what does anhydrous mean? It means without water. So state why anhydrous calcium chloride is added. If it's anhydrous, it can become hydrated calcium chloride. Why would we add something that's anhydrous? To absorb water. It is a drying agent. So what that means, it can remove all of the water. It will clump together, it will soak up the water and become hydrated calcium chloride. So it's a drying agent. So great if we're purifying this and we want to remove the water, add some calcium chloride. It's one of those typical drying agents that will remove the water. Super duper duper. Let's zing. I think this question's nearly done. What we got left? Oh, we got an amount of substance question. Right, 1.7. A student uses the method to prepare some ethyl ethanoate. So again, we've got ethanol, ethanoic acid, ethyl ethanoate, water. The student adds 10 centimeter cubed of ethanol, MR46. So as soon as I read through this question, I'm thinking to myself, these guys just mentioned MR. It's the weirdest looking triangle I've ever made. It's like a witch's hat. Right. I'm immediately thinking mass over MR times moles. The student adds 10 centimeter cubed of ethanol. We got the MR is 46 to 5.2 grams of ethanoic acid. So I'm going to group my data together to make it easy. You can do this. Some people like this. So I've got 10 centimeter cubed ethanol. And I know the MR is 46. So that's my data for the ethanol. And then they're giving me data for the ethanoic acid. So I've got 5.25 G of ethanoic acid. Let's not have the pain of watching me write that out. So let's type that out. So I've got 5.2 fam grade ethanoic acid, and that has an MR of 60. And then our product that's produced, we obtain 5.47 grams of ethyl ethanoate. And yeah, so we're going to get 5.4, hold on my days, 47 grams ethyl ethanoate. This is our product, and that's got an MR, yikes, of 88. So what do we want to do here? Oh, we're also told the density of the ethanol. So let's whack that in over here. Density ethanol. So I'm grouping all my data together. Some people, this is just a technique. I don't often do this, but this is something that some of you might find useful. Just to group your data together so you know what you're working out. So I now got the density of the ethanol. Determine the limiting reagent. So which of the two reactants are limiting? So first of all, that's going to pick us up some marks. So I'm just going to circle my reactants are the ethanol and the ethanoic acid. So that's this data here is one of my reagents and this data here. And then calculate the yield of ethyl ethanoate. Now, if I zing over here, you can see this is my product, the ethyl ethanoate. So that's that data. So first of all, let's calculate the moles of each of these and then see which one we don't have enough moles of. That's going to be the limiting reagent. You might say to yourself, I need to know the coefficient and the reaction. We can see from this, it's a 1-to-1 reaction, right? There's 1 mole of ethanol reacts with 1 mole of ethanoic acid. We can see it from that equation they've given us. So we know the ratio is 1-to-1. Let's work out the moles of each. So I'm going to start here with the ethanol. We have 10 centimeter cubed and an MR of 46. I can't quite use this. I don't have the data to use N over C times V because I don't have the concentration of that ethanol, but I do have the density. So if we know the density equation, D equals M over V, you need this in a lot of chemistry. I need the mass, because then I can use it with the MR of the ethanol. So I'm going to do density, which is 0.790, 0.790, and I'm going to multiply that by 10, which is the volume. So I've got D times V, we've arranged that, and that's going to equal my mass. And our mass is going to be 7.9 grams or 7.90 grams. So we've just found out how many grams we've got, and potentially that has garnered us our first mark. Now I need to use that and the MR, mass over MR. So I'm going to divide that by 46, and this is going to give me my moles of ethanol, and it's 0.172. So I've got my lovely moles of ethanol right there. The next stage, what I need to do is work out my moles of the other reactant, and then the first thing we can do is note down the limiting reagent. So my other reactant is really easy. I've got 5.25 and 60. So let's do, so this was for ethanol. Always good to keep up and make sure you know what you're doing there. Now for ethanoic acid, I want to do, what was it, 5.25 G, divide that by 60. Let's whack that in the calculator, and that gives us 0.0875 moles. So you tell me, what's bigger, 0.172 or 0.0875? Hopefully you realize that 0.0875 is smaller. So my limiting reagent is ethanoic acid. I'm going to be left with a certain moles of ethanol left over. Now, if I wanted to find out how many moles of ethanol I've got left over, I could do 0.172 minus 0.0875. And I'm going to find out exactly how many moles of ethanol we've got left over, but we don't need to find out how much ethanol is in excess. That's not part of the question. The next part of the question is to calculate the percentage yield of ethyl ethanoate. So I know that the maximum amount of ethyl ethanoate I can make is limited by the amount of this. It's a 1-to-1-to-1 reaction. So if I've only got 0.0875 of ethanoic acid, then I can only make 0.0875 of ethyl ethanoate. I can't make 0.172 because I don't have enough ethanoic acid. So let's find out how much ethyl ethanoate we would actually make. And I can come here and I can do that by taking the MR of ethyl ethanoate, which is 88, and I can multiply that by the moles, N, 0.0875, and that will give me the mass. So let's see what the maximum, can't spell, maximum mass of ethyl ethanoate. Oh my gosh, it's all in caps. Let's get rid of that. Maximum mass of ethyl ethanoate produced, or maximum mass of ethyl ethanoate, it's going to be 0.0875 moles times 88. What does that equal? Smash that in the calculator. Oh my gosh, where's my calculator? So 0.0875, oh geez Louise, 0.0875 times 88. So maximum ethyl ethanoate is 7.7 grams. Now, hopefully you know your yield calculation. Yield equals actual divided by maximum times 100. So let's do that. So we want to do that actual over maximum. So the actual mass we made was 5.47. So let's do that. So we're going to go 5.47. That's our actual mass of ethyl ethanoate produced. It's set it up here. You obtain 5.47. Divide that by our maximal mass, 7.7. We want to times that by 100. And I believe that's going to be about 70%. So let's go that 5.47 divided by answer equals that times 100 equals 71%. 71.03, whatever. I'm leaving it at 71%, and that is our percentage yield. Nice. Awesome. So a lot of marks on display here, 5 marks. Probably get 1 mark for the density calculation, 1 mark for working out the moles of ethanoic acid and saying that that's the limiting reactant by comparing it to the 0.172. 1 mark for working out the maximum mass, so that we're up to 4, and then 1 mark for the yield, and that's going to be 5. Okay. Okay, the final question here is suggest a reason why the percentage yield is not 100%. So why is our percentage yield, why is it not made 100%? So what you've got to do is look back up here at what we're using. So why is our yield not 100%? What do you know? And this is just some of your content knowledge about ethyl ethanoate. What type of molecule, what family is ethyl ethanoate? Hopefully, you know, ethyl ethanoate is an ester. Do you remember the three bits of like kind of knowledge about the uses of esters you've got to know? So you've got to know that esters are good in the food industry because they've got nice smells. They're good in perfume. And why are they good in all those things? Because they're quite volatile and they evaporate easily, which means like they're great for perfumes and great for like flavoring sweets and things like that and adding smells to things. Ethyl ethanoate, I think, is the one that smells like pear drops, maybe, or maybe that's a different ester. But yeah. So one of the things I would suspect is we've probably made close to the actual yield, but if we left it around for a few minutes, all the time we're leaving that product there, that ester, it is evaporating and our mass of product is decreasing. So ethyl ethanoate is volatile, so is evaporating. So um, product lost through evaporation. You get that with some of these organic solvents. So there we go. It can be a good thing in certain situations in chemistry. Okay, boom. That's the end of the first question. How did you do?
You're still here? It's over.